Welcome back. I am absolutely thrilled to share this explainer with you today because we're diving into one of the most foundational and honestly coolest techniques in all of computer science. It's called backtracking. If you've ever wondered how software solves crazy logic puzzles or how AI systems navigate a massive web of rules without just completely crashing your computer, well, you're in the exact right place. Let's get into it.
Think about the last time you were working on a really brutal jigsaw puzzle, or maybe you were trying to navigate a physical maze. You pick a path, you walk down it, and eventually, bam, you hit a dead end. So what do? You definitely don't start the entire maze over from the very beginning. No way. You just back up to the last intersection where you made a choice and you try a different path. It's a totally natural human behavior, right? Well, guess what? We can teach computers to do the exact same thing.
Now, in our previous explainer, we talked about plain recursion, a function calling itself to break down a problem. But backtracking, it's a massive step up. It is essentially recursion with judgment. It's this systematic trial and error algorithm that explores potential paths, and here is the absolute magic part, it abandons a path the very moment it realizes that path violates a rule. It literally knows when to give up, which saves just an incredible amount of time.
Okay, let's dive right into our roadmap for today. First, recursion with judgment. Then, the logic of backtracking. Third, real-world applications. Fourth, common misconceptions. Fifth, why backtracking matters. And finally, the next step.
Chapter 1. Recursion with Judgment.
So look at the stark contrast between these two. With plain recursion, the algorithm blindly explores all possible paths to their absolute end before deciding if they're correct. It just tests everything. But with backtracking, it's actively evaluating as it goes. As soon as a rule is broken, boom, it stops, it retreats. In computer science, we call this pruning. It cuts off the dead branches before wasting precious computing power on them.
Chapter 2. The logic of backtracking.
There's this really rhythmic three-step mantra to backtracking. Step 1, choose. You make a choice that might lead toward a solution. Step 2, explore. You recursively move forward with that choice, but if you hit a dead end, you move to step 3, unchoose or undo. This unchoose step is the absolute hero of the technique. It explicitly undoes that last move so the system can cleanly try the next available option.
Let's see how this actually works using a classic example, the n-queens problem. Imagine trying to place 8 queens on a standard chessboard so that none of them can attack each other. The algorithm places a queen in the first row. Then it moves to the second row and tries a column. It immediately checks for validity. Are they in the same column, same diagonal? If there's a conflict, that placement is invalid. The algorithm unchooses that square, picks the queen back up, and tries the next column over. It never even bothers placing the third or fourth queens if that second one is already in an illegal spot.
We see the exact same logic when solving Sudoku. To fill a 9x9 grid, a backtracking algorithm acts a lot like we do. It tries placing a number, say a 1. It checks the row, the column, and the little 3x3 square. If a 1 already exists, well, the constraint is violated. It backs out, unchooses the 1, and tries a 2 instead. Python programs literally use this exact technique to solve Sudoku puzzles in milliseconds by dynamically adapting to the constraints of the board.
And all of this brilliantly illustrates the overall tree search intuition. You can actually visualize every backtracking problem as a massive, downward branching tree. Every choice splits into more branches, but because of that hero unchoose step, the moment a branch becomes invalid, it grays out. It gets satisfyingly pruned away. The algorithm just folds right back up the tree to the last valid fork in the road and continues down a fresh path.
Chapter 3. Real-world applications.
Out in the real world, backtracking is the core engine for solving what we call constraint satisfaction problems, or CSPs. A CSP is simply a mathematical puzzle where you have variables, domains, which are just the possible values, and constraints, which are the rules. The whole goal is to find a state where every single variable satisfies all the defined constraints simultaneously.
So this isn't just some neat trick for puzzle games. It saves real time and serious money in enterprise software. Think about massive scheduling systems, like exam timetabling, meeting scheduling, or hospital staff shifts. The variables are the resources, the domains are the time slots, and constraints are rules like nobody can work consecutive night shifts. Or take telecommunications. Telecoms use a variation of a classic CSP called map coloring to allocate radio frequencies to cell towers so they don't interfere with each other. From logistics and delivery routing to optimizing financial portfolios under strict risk rules, backtracking is working behind the scenes to assign constrained resources efficiently.
Chapter 4. Common misconceptions.
Time to clear up some myths.
The first myth is that backtracking is just the exact same thing as recursion. But as we saw earlier, backtracking actually prunes invalid paths early instead of just exploring everything blindly. The second myth is that it's always slow. Now sure, in the absolute worst case scenario, the time complexity can be exponential. But the reality? We use smart heuristics to make it incredibly efficient. For example, using a heuristic called minimum remaining values, the algorithm automatically chooses to evaluate the variable that has the fewest valid options left. By ordering the variables smartly and using constraint propagation to basically look ahead, the algorithm prunes massive sections of the search space instantly.
And myth number 3, backtracking always finds the optimal solution. Actually, that's false. Backtracking is designed to find valid solutions that satisfy all the rules you gave it. It just wants a configuration that works. If you're looking for the single, absolute best, mathematically optimized path, say the absolute shortest route on a map, you'd likely need to turn to something like dynamic programming or greedy algorithms, not pure backtracking.
Chapter 5. Why Backtracking Matters. So why should you care about all this? Well, first, it's the absolute foundation for constraint satisfaction problems, which, as we just saw, essentially run the modern world's scheduling and logistics. Second, it's essential for AI search techniques and for really understanding how complex software makes rule-based decisions. And practically speaking, it's a classic focus in technical interviews. If you're interviewing for a software engineering role, you are highly likely to encounter n-queens, Sudoku solvers, or string permutation problems. Mastering that choose, explore, unchoose rhythm literally empowers you to ace those whiteboard tests.
Chapter 6. The next step. We've built upon our previous explainer on plain recursion, and you can really start to see how this is all building toward a full series on how algorithms actually think and make complex decisions. If algorithms can learn to intentionally undo their mistakes to find the right path, what complex puzzles can you solve by applying that exact same logic? Be sure to follow along for our next explainer as we continue exploring algorithmic decision-making.
Thank you for watching the Tech Canvas. Complex ideas, clear pictures. Follow for more.